All right, welcome back. So the last thing we have to do this semester is talk about one more type of problem, which brings us back to solving systems of inequalities, which you guys did pretty well on. It's something called linear programming, but we don't really need to know what it's called to do well on it. You've done this problem before, the one that's in the black text. The blue equation, the blue question is new, and that doesn't really change what you do up to that point. It just adds one more step. So let's first figure out what's going on. We got a furniture store that sells chairs and tables. It sells chairs for $100 each, tables for $600 each. Every day, the store can ship no more than 30 pieces of furniture, and they must sell at least $7,400 worth of chairs and tables. And they can't sell, I'm sorry, they can sell a maximum of 10 chairs. So 10 is the most they can sell in terms of chairs. X is going to represent the number of tables, not the profit, or not how much tables are sold for. We know that tables are sold for 600. The thing we don't know is how many tables are there. So X is the amount of tables, Y is the amount of chairs. And whenever I read that, I definitely write it down. You'll have to write it down too, because we've got one more midterm problem to solve. And it won't tell you explicitly what X and Y are. You'll have to identify that on your own. X is going to be the amount of tables, Y is the amount of chairs. So as an ordered pair XY, I know that that's going to be tables, chairs. And what's new is the profit of a chair is $45, and the profit for every table is $188. This is just how much they sell for. They sell for $100, but the furniture store keeps 45 of those dollars. That's the profit. The other 55 would just go towards all the costs of the store. And for tables, they sell for 600, but the profit is 188. So the most obvious question would be, how many chairs and tables should we sell to maximize our profit? So that's the last thing we do. So this should look very familiar to you. We're just going to solve this portion up here. And the first part, sell for $100 each, tables sell for $600 each. Okay, that's fine, but I can't really do anything with that right now. I could write this, but this is an expression, 100 times y plus 600 times x, because chairs are for $100 and tables are 600. But this right here, this expression tells me all the money I am kind of selling, all the money that I make based on the sales alone, just based on selling 100y plus 600x. It's the second sentence that allows me to write my first constraint. The store can ship no more than 30 pieces of furniture. So all the tables that I sell plus all the chairs that I sell, how is that related to 30? Well, it doesn't equal 30. It doesn't say that it has to sell exactly 30 pieces. It just can't ship more than 30. So it can't ship 31. It can't ship 32. So it has to stay under 30, but of course it could equal 30. So x plus y has to be less than 30 or equal to 30. And they want to sell at least $7,400 worth of chairs and tables. So this is how much I'm selling, and I want that to be greater than or equal to 7,400. And then finally, the store can sell a maximum of 10 chairs. So y is the amount of chairs that they sell. So I'm talking about y only. How is that related to 10? A maximum of 10. So y has to be under 10 or it could equal 10. So here are my three constraints. So now let's go to Desmos and graph these guys. One was x plus y is less than or equal to. So if you press the less than or and then equal to button on your computer, it should just converge to that. X plus y is less than 30. So let me zoom out. All the ordered pairs of the shaded region, the x value plus the y value is less than or equal to 30. The other one was 100y plus 600x has to be greater than or equal to 7,400. So every ordered pair in the red section If you take 100 y's plus 600 x's, you'll get a number that's greater than 7,400. And there's one more. The y has to be less than or equal to 10. And then, well, when we studied this before, you just had to pick one ordered pair in the region that was shaded by all the constraints. So anything in here, like this is a 15.5 is a great ordered pair. 15.5 would work because I forget already what X was. X was tables. So if we sell 15 tables and 5 chairs, we will do it. It's under 30 items. We're going to make at least 7,400, or that's how much we're selling. And then the amount of chairs is under 10. So let me just copy and paste this. Actually, before I copy and paste it, I want to find out the blue question. How much I max? What's the special ordered pair that maximizes this profit? So here we introduce a new equation. So I call it the profit function, and it depends on x and y. So you could even write a function of two variables, x and y. You don't need to do that, but don't want to confuse anybody, so let's just leave it alone. P for profit equals $45 per chair. Well, chair was y, so 45y plus 188x. That is my profit equation, and I want this to be maximized. Remember when we had an order pair 15.5 was a solution? Well, if I do sell 15 tables and 5 chairs, then what's my profit? Well, 45 times 5 plus 188 times 15. I go to my calculator. 45 times 5 plus 188 times 15 equals 3,045. So if I sell 5 chairs and 15 tables, I will make a profit of $3,045. That's enough to go to the movies when they open. But is this the greatest profit I could possibly get? Is it the greatest one? I mean, I just randomly chose 15.5. What if I chose 25? Is that more or less? Well, luckily for us, there is a theorem. When we try to maximize something or minimize something, it's going to be, oh, come on, I can't highlight all these. It's going to be at one of the vertices. So a vertex is when you turn the corner on the shaded region. So if there's a maximum or a minimum, it's going to occur at one of these vertices. And I checked 15.5, which was right in the middle. This is called the feasible region. But I want to find the maximum. In other problems, we'll have to find the minimum. But wherever the maximum or the minimum is, it's at one of these vertices. It's actually at one of the vertices or every point between two vertices. But that's we don't care about that right now. We're just going to focus on the vertices. And this is what I'm going to copy and bring over. Come on. Okay, my profit equation was this. Computer's not fast enough for me. It keeps on freezing up. So since there are only 4 vertices, I just had to do this equation 4 times and see which one, and just observe which one is which. So, okay, now right away, 10.667, I forget already, is X is tables. I can't have 10.667 tables. So we'll just make this, now do I make it 10 tables or 11 tables? We will do 11 tables. And because I want to be kind of in the feasible region. So if I go to the left, if I make it 10 tables, I'm going to the left, I'm going away from the feasible region. So I made 10.667. I raised it to 11. So I went to the right, getting me closer to the feasible region. So we're going to test 1110. And so that's P equals 45 times 10. 45 times Y, don't get mixed up. 10 is the Y, plus 188 times 11. And that equals, go to my calculator, 45 times 10, 2,518. Okay, not as big as the 15.5 one. Let's try this, 2010. 2010. So P equals 45 times 10 plus 188 times 20. And I go to my calculator. And I get a whopping 4,210. So far that's in the lead. But I have to test all of these. Let's try 30, 0. So 30 tables and 0 chairs. Is that what that means? So 45 times 0 plus 188 times 30. Oh, 5,640. One more to go. There's one more vertex to go, and it's this, 12.33. Now, what do I round this to? Because you can't make 12.33 tables. Well, if you said 12, I would have to disagree with you. Because, quote, mathematically, you would round down to 12, but you have to think of the context of this problem. 12 chairs is not going to be good enough because here's the feasible region, this section right here. If I make 12.33 12, I'd be going to the left. I'd be going away from this feasible region. And so I had to go to the right. So I had to actually round this to 13. And I think this is something we'll have to talk about in class tomorrow when we see each other. So P equals 45 times the Y value plus 188 times the X value. And without even touching my calculator, it's got to be less than 56,400 because this is 188 times 30. We'll just do it for our sake, 2,444. Now, the beauty about this theorem is that there are many ordered pairs in here, but I don't have to check many ordered pairs. I can have faith in the theorem that the maximum is 5,640, which occurs at 30, 0. That was a vertex. You find all the vertices and you check each vertex. So the results, I already forgot, tables and then chairs. So this company, if you were working for them, should sell 30 tables and 0 chairs to maximize their profit. That is the end result. So in other words, chairs don't really matter in this scenario. Hopefully that makes sense.